Now that we have seen how to use substitution to find antiderivatives, in other words, indefinite integrals, let's take a look at what this means for definite integrals. So we have seen that we can find an antiderivative of a function of the form g of f of x multiplied by the derivative of f, derivative of the function inside, using this substitution trick. You let u be f of x and you rewrite the integral under a form that is easier to handle, but it's an integral in terms of a new variable. Because of the Fundamental Theorem of Calculus, we know that under the assumption that the function we integrate is continuous on the interval of integration, all we need is an antiderivative of that function. Therefore, we expect this substitution rule to apply to definite integrals, at least in the case where the function we integrate is continuous on the interval. So here is the form that it takes in the context of definite integrals. The integral from a to b of a function of the same form, so a composite g of f of x multiplied by the derivative of the function inside, f prime, is going to be the integral of g of u du, where u is f of x, so just the same thing as the case of the indefinite integral. But we have to change the bounds of integration. A becomes f of a and b becomes f of b. This is because on the left-hand side, we integrate with respect to the variable x, and the bounds of integration a and b give us the interval of values that are assumed by the variable x. On the right-hand side, the variable of integration is u, and we have to give the corresponding interval of values that the variable u assumes when x takes values between a and b. The assumptions for this to be true are essentially assumptions we need for the Fundamental Theorem of Calculus to apply. For this theorem to apply, we need the function that we integrate to be continuous, so we're going to assume f prime to be continuous. And then the second part of the condition, that g is continuous on the range of f of x, is simply to make sure that the part g of f of x is also continuous on AB. So just a sketch of proof for that. Let capital G be antiderivative of the function little g. Then using the chain rule, it is clear that this capital G composed with f of x is an antiderivative of little g of f times f prime. This is just a chain rule. And under our assumption we have continuity of the function we integrate, and therefore the Fundamental Theorem of Calculus applies. So that means that this integral is going to be simply the difference of the values of an antiderivative between a and b, and we found an antiderivative, namely capital G of f of x. So if we plug these values in, we obtain g of f of b, capital G of f of b minus capital G of f of a, but I can rewrite that as capital G of u that I evaluate between f of a and f of b, and that's the integral that we have on the right-hand side in this new substitution rule. So now let's take a look at some examples to see how this is used. Let's start with the integral from 0 to root pi of x cosine of x squared. We're going to proceed as usual, look at the composite part, in this case cosine of x squared, and take for u whatever function is inside, so in that case x squared, and then calculate du. Du is 2x dx. Then as usual we try to match with what we have inside our integral. So here I have x dx instead of 2x dx, so I'm going to solve for that, and x dx is 1/2 of du. So we're going to be able to replace x dx by 1/2 of du and cosine of x squared by cosine of u. So we obtain that the indefinite integral of x cosine x squared dx is 1/2 integral of cosine u du. So far, just the same thing we were doing before. However, what we want is not the indefinite integral, but the definite integral from 0 to root pi. So how do we change the bounds? Well, we're going to look at the expression for u. U is x squared. The integral on the left hand side from 0 to root pi of x cosine x squared dx, x takes values between 0 and root pi. We need to look at what it means for u. So when x is 0, we plug x equals 0 in the expression for u, we get u is 0 squared, that's again 0, so the lower bound of integration is 0. On the other hand, when x is root pi, then u is root pi squared, that is pi, so the upper bound of integration is going to be pi. So now we have a definite integral from 0 to pi for cosine u, and cosine is of course continuous, so we can use the fundamental theorem of calculus to the effect that this integral is 1/2 of sine u that we evaluate between 0 and pi. And since sine pi and sine 0 are both 0, we obtain 0. Looking at this second example, we want to integrate from 0 to 1 the function 1 over 2x minus 3 squared. Now here I just want to mention that this is important that this is between 0 and 1 and not 0 and 2, for instance, because we're going to apply the fundamental theorem of calculus at some point, and we know that this applies when the function that we integrate is continuous on the interval of integration, so on the interval 0, 1. You see that the function 1 over 2x minus 3 squared is continuous everywhere except when the bottom is 0, that is at x equals 3/2. Here we have no problem because x equals 3/2 is not between 0 and 1. If we were integrating between 0 and 2, then the interval would include the point x equals 3/2 and we would have a problem. And this type of problem is something that you will look into in Calc 2. So in this case, we proceed as usual. We look at the composite part. We have 2x minus 3 that is plugged into the power negative 2 function. So we let u be 2x minus 3 and calculate du, which is 2 dx. What we have in the integral is dx, so I solve for that. I get dx is 1/2 of du. So we'll be able to replace dx by 1/2 du and 1 over 2x minus 3 squared by 1 over u squared. So we get that our antiderivative of the function we want to integrate can be written 1/2 integral of du over u squared. Now if we look at the definite integral, then we have these bounds of integration from 0 to 1 for x, and we need to look at the expression for u to see what that means for the range of values assumed by u. More specifically, when x is 0, we plug x equals 0 in the expression for u, we get 2 times 0 minus 3, so u is negative 3. On the other hand, when x is 1, I plug x equals 1 in the expression for u, I get 2 minus 3, negative 1. So the lower bound of integration is negative 3, the upper bound negative 1. Now all I need is an antiderivative of 1 over u squared, because the fundamental theorem of calculus applies to this new integral, because 1 over u squared is continuous on the interval from negative 3 to negative 1. So 1 over u squared is simply u to the negative 2, so an antiderivative is u to the negative 1 over negative 1. In other words, negative 1 over u. So we obtain that this integral is equal to 1/2 multiplied by the function negative 1 over u that we evaluate between negative 3 and negative 1. Plugging values in, we get 1/2 of the value at negative 1 is 1, the value at negative 3 is 1/3, so we subtract 1/3 to 1, we get 2/3, dividing this by 2 we obtain 1/3. For the third example, we integrate from 0 to pi over 2 cosine x multiplied by sine of sine x. As usual, we first focus on the composite part to try to find out what a new variable u should be. This is what is inside, so here we plug sine x into the sine function. So we pick for u sine x, we calculate du, it's cosine x dx. In that case, this is exactly what we have. We have cosine x dx, that's du, multiplied by sine of sine x, that's sine u. So we rewrite our indefinite integral as integral of sine u du, and then to interpret what that means for the definite integral from 0 to pi over 2, Again, we look at the expression for u. When x is 0, then we plug that in u, and we obtain sine 0, which is 0, so the lower bound of integration is 0. On the other hand, when x is pi over 2, we plug that in the expression for u, we get sine of pi over 2, that is 1. So we obtain the integral from 0 to 1 of sine u du. Sine, of course, is continuous on the interval 0, 1, so by the fundamental theorem of calculus, we just need to evaluate an antiderivative of sine u between 0 and 1. An antiderivative of sine u is negative cosine u. We plug the value at 1, we get negative cosine 1. The value at 0, we get negative cosine 0. We subtract that. Cosine 0 is 1, so we obtain 1 minus cosine of 1. Of course, here, angles are measured in radian, so this is negative cosine 1 radian, whatever that value is.